Thanks for the opportunity. I'm not really a presenter. I'm a chemical engineer that like to spend my time in laboratories and invent things and try and do the impossible. The whole technology started back in 2002 in Africa, South Africa. I think from my accent you can hear that I can do a braai better than what you guys do a barbecue, being South African. But we started with building, initially fixing and repairing roads for all the remote and, you call them outback areas, rural and remote towns. And then more so for the mining industry, which the little brown picture on the right-hand side there, that's mining haul roads stabilized with up to 15% of biochar in those roads. So we developed anionic emulsion, high pH, obviously environmentally friendly or environmentally safe. And this emulsion, bitumen-based, but no heat, no solvents. The technology is based on forming covalent carbon bonds. So we use the same aggregates or the same soils and gravels as what the hot mix asphalt guys use, the cement guys, your normal cement construction. But we need a carbon source to form those covalent bonds. Your general hot asphalt applications are based on ionic bonds, which is a bit weaker, a lot weaker. Covalent carbon bonds, that's what sits in the diamond. At the same time, it is not an adherence or it's a coating. Your normal bonding mechanisms is based on adhering or surface coating. Ours is a penetration bond. So we need carbon and we need a bit of moisture because the covalent bonds with capillary action chases right into the structure of aggregates. Our emulsions bonds to steel, it bonds to glass, everything. So initially we used carbon coal fines, all the unwanted carbonaceous shales, your hang wall and footwall portions from the coal industry. And we got the business going all throughout third world countries, Africa, then up in Vietnam. We are fairly substantial. We have 3 big production plants in Vietnam. Malaysia, Thailand, and then from Malaysia we actually exported the product to 14 countries because the material, as you can see in the bottom one there, that's a road we did in the Barossa, in Adelaide area. We shipped that material all the way from South Africa. So we can take the coal premix and if you stick it in a 25 kilo LDPE bag, it's good for 2 to 3 years. If it's in a bulker bag, 6 months to a year. If it's in loose bulk on the back of a tipper lorry, it can travel for 2 weeks into the bush and you can build a permanent road with the lightweight compaction equipment needed only. So the swing came in 2014 because in Malaysia we did not have, there's no coal, availability of coal or coal fines in Malaysia. Everything is imported from Indonesia. So we had to look at another source of carbon and biochar came to light. Now if you asked me in 2014 what is biochar, then I also would have said I don't know. But we found out, and lots of R&D, lots of development, performance testing. It is now very well known in the world that biochar additions to construction materials gives much better performance, longevity, etc. So we've switched the whole organization over from utilizing coal fines to biochar. We have the vision, we have the missions, we're passionate about making the world a better place. We have the ability to utilize co-pyrolyzed material. Obviously, we're going to leave the good, clean feedstocks for the good, clean processes. to produce good, clean agricultural char, biochar, feed-grade chars. But even in those processes, there's a lot of byproducts or waste coming off that is either under spec or contaminated with heavy metals because you've had some sewage in there. You know, heavy metals, there's no more clean water in this little earth of ours. Everything, even the rain falling in Iceland, is contaminated already. And if it's not heavy metals, then it's micro and plastics. Micro and nanoplastics, they're everywhere now. So we said if we can utilize non-organics, municipal waste, that specific one is heavy gauge tarpaulins that's used in the grain industry and the canola industry, these big heaps that they cover over. These things are landfilled because it's too difficult, it's too contaminated to reuse. So we started doing co-pyrolysis, the top picture, started co-pyrolysing harvest waste, contaminated foodstuffs, biosolids from the cow and horse industry. Then did some projects working with the water treatment guys over in Sydney, and you know the normal sewage systems. If you pyrolyze biosolids, you end up with a very low carbon content material, which normally needs to be. It's just not enough or commercially viable to turn that into energy. So they landfill it because it's heavily concentrated and contaminated. We've put that into the road systems. We've done the leach tests, leaf tests, everything to make sure we don't contaminate groundwaters and lock it up inert. So the test work has also been done now to prove that when we put biochar into the road systems, they stay there for 1,000 years. We'd like to say 1,000, but so far the carbon trading platforms that links this into a carbon credit, they say, okay, hundreds of years, we'll give you this in the meantime. So the ability to start cleaning Mother Earth at scale is now there. Your production of standard agricultural grade and feed grade biochars are obviously a slow process. It's very limited in the world at this stage of the game because equipment's expensive. Specifications to utilize biochar, you know, if you want to plant your tomatoes into it, it needs to meet some very stringent specifications. And it's expensive to get it to that clean state. We say, from our side, we can use partially pyrolyzed biochars, we can use co-pyrolyzed, and we've taken, I think, about 167 different types of biochars now, and we put them into soils and gravels and concrete aggregates and proper quarry aggregates. So all those samples, we make up samples, Marshall Core samples, and we have that tested both for leaching and for performance. We can now build high-duty, low-speed roads in the middle of nowhere, utilizing local soils and gravels. So now you don't have crushing and blasting and crushing and screening for aggregates that need to travel, you know, hundreds of miles or kilometers to go and build a road somewhere. We use the local soils and gravels that's in the area. We add the emulsion, and we add up to 15%. We can go to 25%, but I'm limiting everything now to 15% of biochar. Every ton of biochar that's in the road can be equal to up to, well, we've done some test work, up to 2.9 carbon credits, and the voluntary carbon credit values in the world now, every now and then Microsoft buys a bundle of it at $500 over per credit. So performance-wise, I mean, this presentation will be on the website as well. Any questions on performance? We put the material as an overlay, maximum 30 millimeters thick, onto runways. There where the Boeing go and sit down. We've done it. We don't have official airport clearance, but many smaller airports throughout Africa now uses our material as because they can bring the material in, store it, there's no waste, and use it whenever they need to use it. So performance-wise, we've done a lot. And again, that's a photo of the wine regions. There's especially in South Australia, in Adelaide, Barossa, and they have massive silicosis problems because they've been adding high silica containing rocks, gravels and aggregate to their open house haul roads and everything. That silicosis, that silica is now migrated into the vines, into the grapes. It's a much bigger problem than what people think. Our material is up to 40% cheaper per square meter installed compared to hot asphalt. That's why I've got 5 targets on my back, because the ugly sisters, our friends Downers and Fulton Hogan and these guys, everybody wants this technology, but they want exclusivity. And I've put my foot down and I've said, everybody in the world must be able to utilize contaminated or clean biochar if you don't have any other use for it, but to utilize biochar at scale in the construction industry. And that includes road surfacing, road base stabilization, low-cost housing, bricks, erosion control for seasides. We've done them all. I'll go a little bit quicker. That's just a collage of different materials. So this bottom one over here is a mixture of chopped up old ceiling boards, brick wastes, all kinds of waste coming out of it. Dare we say asbestos? You know, that's a bit of a no-no in Australia, but asbestos-containing material, we've put that into a construction product and made it inert. It does not come out again. So, but we tend to stay away from the asbestos side. The top right one, normal laterites, and the lighter soil there was out of the Pilbara area. That's the stuff, if you put a cup of water onto that soil, it becomes quicksand. So we can even stabilize that. The far left is an interesting case where in Thailand we utilized carbon black from the tire pyrolysis industry. So when in Thailand they run massive reactors and plants processing tires. Here in Australia the EPA is too tough, so you know all your tires get exported and processed there, and so we the plant produced bunker oil. So from the tires they go into the reactors. And the main product is a bunker oil. It's like a high sulfur grade diesel type scenario. And the byproduct is carbon black, up to 99-point-something% carbon content, but it's less than 300 micron in size. So it's a huff and a puff and it's gone airborne. And that's the main reason why the processing facilities in Australia is a problem. We utilized that, and we installed a quarry haul road, 1/2 inch thick, 12 millimeters. And that road was installed 7 years ago, I think, and it's still today intact, no creeping, no cracking, no leaching. So any carbon content, biochar, carbon blacks, dust, incinerator, fly ash, bottom ash, if it's got carbon, we can use it in the materials. The process, very straightforward. The emulsion can be produced utilizing small little 4-ton per hour batch plants right up to 40-ton per hour batch plants. Once the emulsion is produced, it can be stored in IBCs. I don't know what you guys call them here, pods or something. Big tanks. To store the liquid bitumen, we don't need any heat, we don't need any solvents. it stays a liquid at ambient temperatures. Being in Kathmandu, sometimes it drops below zero. Once you're ready to use it, you utilize quarry aggregates. If you want to make high-speed, high-duty roads, you need proper graded PSD, particle size distribution, mix designs, same as the hot mix asphalt industry. But you add your aggregates, you add the carbon source, and you add 10% emulsion, give it a quick mix, product is ready to use, or store, or ship, or... the biochar side of it, that little picture is there just to show that because we can use partially pyrolyzed material, you can now take a kiln and double up the belt speed and put in oversized feedstocks, etc. We do not need fully pyrolyzed material. As long as there's an outer layer, carbonized outer layer on the product, our emulsions will grab that carbon and lock it up. So we can even put slightly or partially carbonized wood chips. We put that into roads. Obviously, we're not going to do that on a high-speed road. But mining roads, plantation roads, haul roads, as long as there's a bit of carbon in there, we can use it. If you look at your standard half a ton up to 1 ton per hour feedstock, continuous pyrolysis processes, and there's many in the world. Frank is soon to release a nice continuous system as well, but currently most of them are batch plants. We need to scale up because we need to lock down carbon as much as possible. You know, the weather is going crazy. Because we can use partially pyrolyzed stuff, because we can use feedstocks that normally has to be landfilled. So people come to us and, you know, if they pay $200 a ton to landfill contaminated biomass or, you know, organics and inorganics, we say, no, you know, pay us half the price or whatever. We'll take that. It brings our cost of production down because we are now getting paid to take feedstock. That's why we can produce this road material so much cheaper. But we can also do it at scale because you don't have those stringent quality control process operations anymore. In most cases, we don't need particulate matter cyclones. We don't need scrubbing systems. You know, a simple bag filter system will work because we don't have to go up to 850 degrees centigrade. We can stay around 300, 350, torrefaction, and even below torrefaction-based temperatures. So we can do much more volume. So the business developed here in Australia now already demands about, for the future soil stabilization industry here, we need about 70 to 80,000 tons of biochar at addition level of 10 to 15%. The total biochar production in Australia now is 12,000 ton a year, I think. So we need to start burning things. The more we burn, the more we can clean up. The cheaper we can build roads, the cheaper we can stabilize. And if you then bring investment is now driven by the fact that every oil and gas, Microsoft, all these guys are desperate for offset credits because they can't generate their own carbon credits. So they have to go and buy them from somebody. So apart from the fact that we can clean up, build cheaper, we also create carbon credits. And we've done a simulation at about $540 per carbon credit. The amount of money generated by putting 10% biochar into the road and the carbon credit value of that road is more than the cost of building the road. So we can actually build roads for free. All we need is open the gate, we'll build the road because we'll sell the carbon credits to pay for the cost of building the road. So it's a crazy scenario. Very quickly, Australia, we've done lots of installations as far away as Townsville. The other one is Malaysia. Obviously, Malaysia, we are very, very fully certified. We've done motorways. We've done lots of roads. Myanmar, We exported from the Malaysia plant to Myanmar and installed all over there. Vietnam, we have 3 massive production plants. India, ship about 500,000 bags a year to India. We don't have a plant there yet because we haven't found a good partner yet. So, Timor-Leste, we shipped 300 over containers of material to Timor-Leste, East Timor, and all the coastal roads. Our roads are waterproof, and they don't creep, and they don't crack, and they don't leach. We can handle 10 plus degrees centigrade higher before the material goes plasticity. Hot asphalt, if it's 35 degrees, you don't walk barefoot on the road. Cameroon, that's mining roads. We've done hundreds of kilometers of mining haul roads. Africa, obviously, all over. At this stage, we're continuing sample testing to utilize much higher quantities of crushed glass. Now, glass is supposed to go back to glass because of the energy thing, but if you have laminated glass, you can't reclaim from there. You stuffed. We can put up to 65% of crushed glass into the product as an aggregate because our emulsions bond to it. RAP, reclaimed asphalt products, so all the waste out of the existing roads we can use. That's just the whole greenhouse scenario, and no, that's me. I actually came here to Australia. We landed here in January of 2020. We put a production plant up in Darwin because we couldn't get it happening in Adelaide because of too long waiting times to get an EPA. So it's not only the ARP and the main roads, it's also the EPA side. There is no classification for our plants officially in Australia because they're all hot asphalt, and that takes you 2 years just to get an EPA. That was the first step. The next step, our material, although it's a bituminous-based material, it has the properties of a fixed pavement, not a flexible pavement. So on top of the fact that the EPA side was difficult for us, the test methods that suits all ARP and APFA, they're now APFA. We know the guys, main roads, Vic roads, every single state has got their own road authority. And if you get something certified in Adelaide, in South Australia, which we have the DPTI clearance and sign off for that, if you get it certified there, it means jack shit in, oh sorry, I mustn't say that word. It means nothing in WA or in Vic roads. You have to start the whole process again. So we looked at the whole ARP thing, and that was going to take us 4 years and about $350,000 because the classifications doesn't exist. The test methods does not exist because if they test our material in the lab as the modulus type test work, so your volumetric testing, which is not dynamic testing, it's a volumetric test, static test, then our materials actually fail the test in the lab. But if you install the two next to each other on the road, the hot asphalt and even the fixed concrete pavements, they fail long before our stuff fails. So we had to then develop a brand new test methodology to test for this material that's supposed to be a flexible pavement, but it turns out to be a rigid pavement. I can go technical-wise, I'm not going to, but our materials, for the high-duty stuff, we mix design for 0 voids. Hot asphalt has to have 4 or 5% voids, otherwise it breaks up like glass. So we decided, okay, I'm not going to step on the big asphalt company's toes. We're going to go rural. So mine roads, plantation roads, where it's classified as an unsealed road, and everybody likes it because they get carbon credits, and they get a road that lasts longer. We put a road in for FMG up in the north of WA, and a mining haul, the first road section we put in lasted 9 months through 3 massive rainbout seasons, where their normal roads, with the normal procedures that they do, they have to redo the roads every 3 weeks. Our road went 9 months with zero repair. So, yes, we have a way to walk in Australia still to get this done. But, you know, there is not enough biochar in the country in any case for us to take over all the roads.